This is the lab lecture video for the theory and calculations for the determination of the solubility product constant for an insoluble salt. This one I think wins with the most words in the title. So before we go through the calculations that go with the lab, we're going to talk through the instrument that is used to make the measurements in this lab. And that instrument is called an atomic absorption spectrophotometer and is abbreviated by AA for atomic absorption. Earlier in the semester, you did molecular spectrophotometry, the Beer's law, that you use the cuvette to put the sample in and measured absorbance. So atomic absorption works basically very similarly. We're still going to be, in a way, following Beer's law. The difference is molecular spectrophotometry, the visible spectrophotometry, when you set the wavelength to, 510 nanometers or 447 nanometers, and you poured the solution that had a visible color into the cuvette. That was measuring the absorbance of light by a molecule, not just one element, but a molecule. So yeah, we did an iron lab, but it was actually the iron and the O-phenanthroline. And then we did the FeNCS2+. So we measured iron, but it was iron in a compound. Okay. Well, atomic absorption just measures one element. So whether that element is in a compound or alone, it measures the amount of that individual element, which are in the atom form, right? So atomic absorption is measuring the absorbance of light by a specific element. And so as a general idea, that's how it's different, okay? As an instrument, this is like the inside of the instrument, okay? So the inside of the visible spectrophotometer looked in some ways similar. There was a lamp that I just drew as a light bulb, and then there was a monochromator, which was that filter that you set to whatever wavelength you want. And then there was the cuvette, and then there was the detector, and then there was like the readout. So most of those pieces are here. The hollow cathode lamp is just the fancy term for the light bulb that you use in atomic absorption spectrophotometer. But the monochromator is not right next to the lamp. Instead, there's this flame. So what happens is the element, the atom that you're measuring, it has to be excited into its excited state in order for this light thing to work. So we take the sample and put it through the flame, which then gives it energy, and the electrons are able to be excited, and then it can be measured. Okay, so the pieces are all there, but they're in a different order, and instead of like a glass or a plastic cuvette, it's a fire. Okay. And this isn't really what it looks like. It's not floating, but this gives us the insides of what it looks like. Okay, so the idea of this instrument, we talked about it back in Gen Chem 1 when you looked at emission spectra. You talked about emission spectra when you learned about the first few models of the atom. Actually, take that back. It's the Bohr model of the atom, so the second to last model of the atom. Bohr used this idea to try to prove why his model of the atom was correct, which was that if electrons move from one energy level to another energy level, they either have to absorb or emit light. And he was able for hydrogen to match the colors of light that came out of hydrogen when you run electricity through it, like a hydrogen lamp kind of thing, to the wavelengths that came out. So he was able to map it out. And then it didn't work for helium or lithium or any of the other elements. But every element has its own emission spectra, which is when you run electricity through it, what colors of light come out. So here we have sodium and hydrogen. So hydrogen, we see 4 lines, a purple, another purple, a blue, and a red. And the numbers along the bottom are the wavelengths that those lights would come out. So we see sodium has a very different emission spectra. It's got 2 yellow lines there really close together. Every element has a unique emission spectra. Okay, so that's kind of what we're using to do this, is that each element has specific wavelengths that they can absorb and then emit, and we're able to, as long as we excite the electrons to a higher energy state and let them relax back down. When they relax back down is when they let off the light. When they're excited, that's when they absorb the light. So we're going to be using atomic absorption, which means we're measuring the light that it absorbs for the electron to go from, the first energy level to the second energy level, or the first energy level to the third energy level, not the emission, which is the colors that come out. So that will happen, but we're focused on the energy that it absorbs. So the way this works is we take our sample, which is going for us to be in solution form. It's aqueous. It's going to be a certain molarity of solution mixed with water. And it's going to be sucked up a little like a tube, and then it's aspirated, which means it's turned into a spray, like it's like a spritz, okay? And that goes into the flame, which our flame will be between 2000 and 3000 Kelvin. That evaporates off the solvent, which for us is water. And then the solid, if the the element or the compound or whatever, it breaks it down into the atoms. So if for us, we're going to be measuring magnesium. Okay. Well, if the magnesium was in the formula magnesium nitrate, well, put it in the flame, and what happens is it separates the magnesium from the nitrate and then takes that magnesium and excites it. And so it breaks into the atoms, and then it does the whole light thing that we need to happen. So we don't use an official cuvette. The cuvette is the flame. Okay. And the flame is about 10 centimeters long. But the thing with flames is they're not consistently sized all the time. So we're not going to measure the distance of the flame. So this 10 centimeters, you will never use that as a calculation in anything. So if you use 10 centimeters in any part of this lab, you're doing it wrong. Okay. I probably shouldn't have even told you how long it is, but the hollow cathode lamp is the light source, and we have a different lamp for every element. So we'll have a lamp that we have for magnesium. And if I wanted to test sodium, we would have to get a different lamp. So that's why we don't need the monochromator, which is like the filter thing, to choose what wavelength, because the lamps are made out of the element that we're measuring. So the only wavelengths they have are the correct wavelengths. Okay. And then the detector is going to measure the absorbance. Okay. Just like, and so we still have Beer's law. Okay. So here's just a picture of the lamps. So I mentioned that they're made out of the element that we're measuring. So what happens is it's all about, the ions and releasing, like based on the voltage, and these ions colliding with things and emitting the light. So it's not a big deal that you know the details of this, but do know that each lamp is made for one specific element. Okay, so here's the fire thing. So here's where the hose will be. There'll be a hose right there. And your sample, I'm going to pretend like it's in a beaker. Okay. The sample will get pulled into the hose, and then it goes into this thing. So what happens is here is when it says it's a nebulizer. So it spritzes it. It makes it into a spray. And what we want is we want the tiny pieces of the spray to be each little droplet to be the same size. And so they have this glass bead hanging out right there. And what that does is it stops the droplets that are too big. And then the ones that are small enough make it all the way in through here, which is then mixed with the acetylene in the air, and then it's moved up into the flame, and then the light from the lamp is going here and here, and so it measures the amount of light that is absorbed by the elements that are in there. Okay, so that's just a little bit of a background. It, again, follows Beer's law. We're just using fire instead of a regular cuvette. So I thought this was interesting, the temperatures of the flames. So you don't get to like touch the fire for this because they're between 2000 and 5000 Kelvin, which is hot. Okay, so again, calculation-wise, we're going to be making measurements of absorbances. And just a reminder on Beer's law, C is concentration. For this lab, it'll be molarity. B is the path length, which we don't know for this lab because we don't have a cuvette. And then we have the extinction coefficient. Okay, so that's the extinction coefficient times the path length. And they're both unknowns for us. And then this is the absorbance, which comes from the instrument. Now, what's great about this instrument is more sophisticated. So the atomic absorption instrument is more sophisticated than the visible spectrophotometer. Okay, and it's operated by a computer. So what's wonderful is as long as you do a good job in part A, where you make your standards, as long as you make solutions that their concentrations are correct, you won't actually have to use the Beer's law calculation for this lab because the computer does that math for you. Now, that doesn't mean there's no math for you to do. That's not true at all. But you will be able to not have to make a graph, which is normally how we get our extinction coefficient, and you will not have to use Beer's law if you do a good enough job in making your solution. So extra incentive to be really careful when you make your solutions. Okay, so that's kind of on the instrument. Now I'm going to switch gears and talk about the point of the lab that we're doing. We're using that instrument, and we're measuring absorbances, but the purpose is for us to get the KSP value of a solid, and the solid we're making and wanting to measure is magnesium fluoride. The magnesium fluoride is an ionic solid that is mostly insoluble with water and only dissolves a little bit. So here's the balanced equilibrium equation. So the KSP expression, products over reactants, So magnesium ion times fluoride ion squared, and then the reactant is a solid, so it's like it's over 1. So our end goal of this lab is to calculate the KSP number, to get a value for KSP. It's going to be small, like times 10 to the negative something, okay? But that's our goal. And our instrument measures magnesium, okay? So we'll be able to get measurements, get values for magnesium from our instrument. Well, our instrument, even though we won't have to make the graph or do the Beer's law calculations, hopefully, the instrument needs all that information. So just like when we did our spectrophotometry lab earlier in the semester, part A, its job is to make standards of known concentrations. So that way the instrument can figure out the extinction coefficient. So in part A, our job is to make solutions that contain magnesium of known accurate concentrations. So you're going to be doing dilutions with magnesium. And for this lab, it's going to be magnesium chloride. Now, I know for part A, if we look at the equation that's up there, there's no chloride. Well, in part A, we're not actually doing that reaction. In part A, we're just making magnesium stuff. We just care about this part. So you're going to be doing a dilution using 250 milliliter volumetric flasks and pipettes. So you will be calculating the molarity of the magnesium using the dilution equation, where one side is the stock solution and the other side is the dilute solution that you're making. So the stock solution, you'll be given the molarity. It says in the lab it's going to be about 0.05. Katrina is usually really awesome and usually gets it right at 0.05000 molarity. V1 is the volume of the stock solution that you're going to pipette into the flask, which is different for each of the solutions. So you'll have to look at the table in the procedure to get that, but it's a different number. M2 is what we're solving for, and V2 is how much solution we're making. Well, you're using a 250 milliliter volumetric flask. So you can't officially solve for this until once you're in the lab room, because this number could be slightly different, but it should be around there. So you're just going to do M1, V1, M2, V2 to solve for M2. And that's how you're going to get the value in the first column on your data table after you write down whatever the number is of this solution, which is where it says actual concentration of the stock magnesium chloride. You're going to write down whatever that number is on the board. Magnesium in molarity, you're doing the M1, V1, M2, V2. So in the data table, there's a spot for the blank, but in the procedure, it does not tell you to make a blank. That's because when we test it, our blank is just going to be deionized water. So the molarity of magnesium is going to be 0. Okay. Second column says molarity or magnesium in ppm. So it's been a little bit. ppm stands for parts per million. It's one of the concentration units we learned back in the beginning of the semester. And there are two ways to solve for ppm. You can get the milligrams of the chemical you're looking at, which for us is magnesium, divided by the liters of the solution, or you can take grams divided by grams times 10 to the 6th. Well, we're making a solution in a volumetric flask, which means we're going to know the milliliters. So the milligrams per liter is going to be more useful for us. So you're getting the molarity by doing M1, V1, M2, V2. Okay, so let's pretend that my M1 from the lab, which is not going to be the same value as yours, so this is my pretend scenario, is 0.05012 molarity. Okay, let's say my V1 was 12.0 milliliters. And then our V2 is going to be 250.0 milliliters. We're trying to solve for M2. So I'd put 0.05012 molarity times 12. We don't know M2 times 250.0. So M2 in this calculation, I got 0.00240. I'm not rounding it. 576. Okay, we'll say that that's my molarity. Okay, that would be my first column in molarity. The second column says in parts per million. So what we need to do is take this number and convert it from molarity into parts per million. So molarity has the units. I'm just going to rewrite the number real fast. Moles of magnesium per liter of solution. And we need to get it into milligrams of magnesium per liter. So our entire job here is to convert moles to grams, grams to milligrams, and then our units will be correct. So 1 mole of magnesium is just the molar mass, which is 24.30506 grams. And we know the relationship between grams and milligrams. So when I do this, moles cancel, grams cancel, milligrams on top, liters on the bottom, that's parts per million. And for this, I got 58.5 ppm. So to go from the molarity to the parts per million, you have to convert each molarity into parts per million. The only thing that's going to change is the starting number. Molar mass of magnesium, always true. Grams to milligrams, always true. So you're just going to have to change those. You are going to have to do the parts per million calculations in part A before you're able to use the instrument. Okay, so you have to do that math before you can use the instrument. The absorbance column is coming from the instrument. So that's not a calculated thing. That is coming from the instrument thing. Okay, now hopefully you will not have to make a graph. Okay, so I'm just going to go through the assumption that you don't have to make a graph. Okay, so let's move over to part B. Part B took a lot longer in the lab, do a lot of stuff, make the solid, rinse it, centrifuge, vortex, all that good stuff. Okay, now you should have written down the temperature by checking the thermometer of one of your solutions at one point. And then the absorbance, which is, so I'm looking at part B, the absorbance row is coming from the instrument. You're going to write that down from the atomic absorption, the AA instrument. The magnesium in parts per million, that should also be coming from the instrument. As long as, if the instrument didn't give you those numbers, that's when you know you have to make a graph. If you have to make a graph, shoot me a message so we can talk about how you're going to make your graph. But you should have the first 2 rows completed, the absorbance and the magnesium in parts per million. That's because our instrument, it makes the concentration unit we had to use was parts per million. That's why in part A we had to turn the molarities back into ppms. The issue though, in part B, we're actually doing the equilibrium problem. We're doing this. Okay. And we're trying to solve for the magnesium concentration, the fluoride concentration, so that way we can get the KSP. But the KSP is an equilibrium constant, which means these numbers have to be at equilibrium. So for this lab, we are going to have to do an ICE table. Now, if you remember, ICE tables, the only units allowed in ICE tables are either molarity or atmospheres. So for this lab, it's going to be molarity. Parts per million is not allowed. So the second row that says magnesium in parts per million, the third row that says magnesium in molarity, you're just going to be reversing the calculation that we just did in part A, where we're going to be starting with parts per million and ending with molarity. So let's say I had 38.21 parts per million from the instrument. So that means 38.21 milligrams of iron per liter. What I'm trying to do is get that into molarity, which is moles per liter. 30506 grams in 1 mole. So milligrams cancel, grams cancel. So now it's moles divided by liters. So we're going to get a number much smaller than, so the parts per million number is going to be much bigger than the molarity number. So mine, I was 0.001572 molarity. Okay, so let's go with that's my molarity that I will write down as the magnesium in molarity for part B. And it says show calculation, so that's what you're showing. Next, we need to write down the fluoride molarity. Well, we're going to be looking at our ICE table. So if we look at our ICE table, you did not start with, so we rinsed off all the magnesium and the fluoride until it was just water and the solid. So that means my initial values of this are 0. This is going to be the plus side. I notice that's going to be 2x. And then my equilibrium number for magnesium, which had to be in molarity, is the number that you calculated from the parts per million. So in my ICE table, I have a whole column that's filled. So I know what x is. Now, fluoride, the instrument didn't measure fluoride, but I do know it's going to be 2 times x. Well, if x is equal to that number, 2 times x will just be that number times 2. So the really difficult math between the magnesium in molarity and the fluoride in molarity, take the magnesium in molarity times 2. What we're doing is we're looking at this relationship. Once you know the magnesium and the fluoride, you're just going to be substituting those numbers in here to solve for the KSP. Yes, you do have to take the fluoride squared. Got to follow that equation. And then do the average and the standard deviation of the solubility product. Okay. So calculation-wise, as long as you don't have to do the graph, they're really not too bad. You made up for it with all the centrifuging and the vortexing, though. The post-lab questions, so for number 4, you do have to know your average solubility product, your average KSP value, before you can do number 4. So don't wait until the last moment. For number 5, you're supposed to look up a KSP value for magnesium fluoride, like looking in your appendix of your textbook, or you can look online, but it needs to be a reliable source and you need to cite your source. And so you're going to look up the KSP value and then do a percent error calculation. You're not going to be graded on number 5 on what your percent error is. You're just calculating it. So if your percent error was 200, all right. If your percent error was 20,000, all right, that's not great, but it is what it is. So just do the calculation, but don't freak out about the number, okay? But all the post-lab questions are related to solubility product and more specifically to this lab. So absolutely let me know if you have any questions as you work through the calculations for this lab.